Friends, welcome to my channel. Dhanesh here. In this video, I am going to discuss about quantum cryptography. Before getting into quantum cryptography, let me discuss what is cryptology or cryptography. Cryptology is the practice and study of techniques for secure communication in the presence of third parties called adversaries. More generally, cryptography is about constructing and analyzing protocols that prevent third parties or the public from reading private messages. Various aspects in information security such as data confidentiality, data integrity, authentication, and non-repudiation are central to modern cryptography. Cryptography exists at the intersection of the disciplines of mathematics, computer science, electrical engineering, communication science, and physics. Applications of cryptography includes electronic commerce, chip-based payment cards, digital currencies, computer passwords, and military communications. Cryptography is the science of exploiting quantum mechanical properties to perform cryptographic tasks. The best known example of quantum cryptography is the quantum key distribution, which offers an information theoretically secure solution to the key exchange problem. Key exchange is a method in cryptography by which cryptographic keys are exchanged between two parties, allowing use of a cryptographic algorithm. The key exchange problem describes ways to exchange whatever keys or other information are needed for establishing a secure communication channel so that no one else can obtain a copy. The public key can be sent over non-secure channels or shared in public. The private key is only available to its owner. The advantage of quantum cryptography lies in the fact that it allows the completion of various cryptographic tasks that are proven to be impossible using classical communication. For example, it is impossible to copy data encoded in a quantum state. If one attempts to read the encoded data, the quantum state will be changed. We call it as no cloning theorem. This could be used to detect eavesdropping in quantum key distribution. Versus conventional cryptography. In classical cryptography, the original text is transformed into ciphertext, which is then transmitted across a channel controlled by a data string called a key. The receiver will be able to get the original information and decipher to the original text only if he is in possession of this key. Classical cryptography comes with two main techniques, symmetric and asymmetric cryptography. However, these cryptography techniques face a threat from quantum algorithms. For example, the famous Shor algorithm is capable of breaking an asymmetric cryptography technique such as RSA and elliptic curve. Another quantum algorithm known as the Grover algorithm is capable of attacking symmetric cryptography. Quantum cryptography, on the other hand, offers safe key exchanges based on the principle of quantum mechanics. The security of conventional cryptography is threatened by weak random key generators, advances in CPU power, new attack mechanisms, and the development of quantum computers. With regard to quantum computer in particular, such encryption is rendered useless. The data encrypted today can be intercepted and stored for decryption by quantum computers in the future. Here's about the applications of quantum cryptography. Quantum cryptography is a general subject that covers a broad range of cryptographic practices and protocols. Some of the most notable application of protocols are going to discuss here. First is quantum key distribution. Next is quantum coin flipping, quantum commitment, mistrustful quantum cryptography, bounded and noisy quantum storage model, position-based quantum cryptography, device-independent quantum cryptography. These are all the applications of quantum cryptography. First, we will known and developed application of quantum cryptography is quantum key distribution, QKD, which is the process of using quantum communication to establish a shared key between two parties, Alice and Bob, for example, without a third party, let's say Eve, learning anything about the key. Even if Eve can eavesdrop on all communication between Alice and Bob, Eve tries to learn information about the key being established, discrepancies will arise, causing Alice and Bob to notice. Once the key is established, it is then typically used for encrypted communication using classical techniques. For instance, the exchanged key could be used for symmetric cryptography. Quantum coin flipping. Unlike quantum key distribution, quantum coin flipping is a protocol that is used between two participants who do not trust each other. The participants communicate via a quantum channel and exchange information through the transmission of qubits. But because Alice and Bob do not trust each other, each expects the other to cheat. Therefore, more efforts must be spent on ensuring that neither Alice nor Bob can gain a significant advantage over the other to produce a desired outcome. An ability to influence a particular outcome is referred to as a bias, and there is significant focus on developing protocols to reduce the bias of a dishonest player, otherwise known as cheating. Quantum communication protocols, including quantum coin flipping, have been shown to provide significant security advantages over classical communication, though they are difficult to realize in the practical world. Another application, that is quantum commitment. In addition to quantum coin flipping, quantum commitment protocols are implemented when distrustful parties are involved. A commitment scheme allows a party, Alice, to fix a certain value to commit in such a way that Alice cannot change that value, while at the same time ensuring that the recipient, Bob, cannot learn anything about the value until Alice reveals it. Such commitment schemes are commonly used in cryptographic protocols. Example, quantum coin flipping, zero knowledge proof, secure two-party computation, and oblivious transfer. Trustful cryptography, the participating parties do not trust each other. For example, Alice and Bob collaborate to perform some computation where both parties enter some private inputs. But Alice does not trust Bob and Bob does not trust Alice. Thus, a secure implementation of cryptographic tasks require that after completing the computation, Alice can be guaranteed that Bob has not cheated and Bob can be guaranteed that Alice has not cheated either. Examples of tasks in mistrustful cryptography are commitment schemes and secure computations. The latter including the further examples of coin flipping and oblivious transfer. Key distribution does not belong to the area of mistrustful cryptography. Mistrustful quantum cryptography studies the cryptography using quantum systems. A noisy quantum storage model. One possibility to construct unconditionally secure quantum commitment and quantum oblivious transfer protocols is to use the bounded quantum storage model. In this model, it is assumed that the amount of quantum data that an adversary can store is limited by some non-constant Q. However, no limit is imposed on the amount of classical data the adversary may store. Based quantum cryptography. The goal of position-based quantum cryptography is to use the geographical location of a player as its only credential. For example, one wants to send a message to a player at a specified position with the guarantee that it can only be read if the receiving party is located at that particular position. Task of position verification. The player, Alice, wants to convince the honest verifiers that she is located at a particular point. It has been shown that position verification using classical protocols is impossible against colluding adversaries who control all positions except the prover's claimed position. Under various restrictions on adversaries, schemes are possible. Independent quantum cryptography. A quantum cryptographic protocol is device independent if its security does not rely on trusting that the quantum devices used are truthful. Thus, the security analysis of such protocol needs to consider scenarios of imperfect or even malicious devices. And Yao proposed the idea of designing quantum protocols using self-testing quantum apparatus, the internal operation of which can be uniquely determined by their input-output statistics. Subsequently, Roger Kohlberg, in his thesis, proposed the use of bell test for checking the honesty of the devices. And several problems have been shown to admit unconditional, secure, and device-independent protocols, even when the actual device performing the bell test are substantially noisy, that is, far from being ideal. These problems include quantum key distribution, randomness expansion, and randomness application. It is on the advantages of quantum cryptography. It is virtually impossible to hack, simple to use, dependent on fewer resources to maintenance, capable of detecting hacking attempts in real time. Quantum cryptography. The adoption of quantum cryptography on a large scale can cause a rise in unemployment, possibility of a change in the polarization of photons, lacks features such as digital signature. Quantum computers may become a technological reality. It is therefore important to study cryptographic schemes used against adversaries with access to a quantum computer. The study of such schemes is often referred to as post-quantum cryptography. The need for post-quantum cryptography arises from the fact that many popular encryption and signature schemes can be broken using Shor's algorithm for factoring and computing discrete logarithms on a quantum computer. Examples for schemes that are, as of today's knowledge, secure against quantum adversaries are Mackey's and lattice-based schemes, as well as most symmetric key algorithms. Surveys of post-quantum cryptography are available. You can go through that. So that's all about quantum cryptography. Thanks for watching. Please like, share, and subscribe. Thanks a lot.